Okay, so this time I wanted to do again a data structure, and this time I was thinking to implement a priority queue because we might need it in a future project with a star. So first I'll do the naive implementation just using a list, and that's it. And then we'll go into using a heap structure, and we'll use like a function that decides if it's a min heap or max heap. We'll have like a compare function, and yeah, stuff like that. So let's see. And as usual, start with main C. Okay, just have the basics. Let's compile it. Perfect. So yeah, just having this really simple thing. Um, so we'll need the DA append structure, like macro that we have. So let's go. I think which project has it? Probably ArcParse should have it. Let's copy. Let's steal it from ArcParse. Okay, and let's go back here. Let's have the structure, or I meant the macro. But there was also the man. I really forgot in which project I had the log error. Mm, I think it's in BF compiler actually, right? Not even here. Don't tell me it's in image filter. I was trying to avoid this exact. Okay, yeah, it was in the utils. So let's copy paste this stuff. Well, how about copy pasting the util.h file itself, like, you know. But anyways, so we don't need this. Yeah, I mean, it doesn't matter. We'll copy paste this stuff anyway. So we have the basic stuff. Now let's start with. So yeah, basically what's a priority queue, right? So let's uh, let's go on the drawing board first. So basically, let's say we have some values, and each value has let's say a priority like this. These are the priorities that we have for different types of things. I'm not sure, whatever, can be anything, right? And we want to say something like, okay, give me the item with the highest priority, and we get this one. And then like we delete it. Then the next one is this one, right? And so the easiest way to do it is just put everything into a list, and then when we get the items, we search for the maximum one. So insertion will be O of 1, and when we get the item will be O of n. Now, um, since this looks a bit like you know, binary search problem, this gives us some hints that there might be a solution in of log n, which is a bit, I mean, it's much better when you see the comparison. Um, Although, yeah, like the computers are so fast, it doesn't matter if we do it with a list or with the heap. So, yeah, basically this is the idea. we somehow know that there might be a solution of log n to get the items, and the insertion also of log n. So, but it's still better than linear search. So first, let's do the solution where we just use a list. So we already have the, I mean, if you don't know about this, I think I explained it in the first, I don't remember exactly, but yeah, it just reallocs the entire array when you run out of what capacity? Yeah, out of capacity. So let's create our priority queue. Let's say priority queue, and we're gonna use, like, since this implementation will throw it away when we do the heap, let's just do ints, like, doesn't matter. So the next step is to have an init for our structure, right? Have the init, and then let's say we do a queue where we search for the maximum, right? So the queue, and usually you say, I think, insert, I'm not sure, let me check. Well, oh, insert and pull, let's call them insert and pull just to, I don't know if it's the, so insert, we have the pq and an item, and so we just do the append. Okay, let's put them as void because we don't care, and we need stdlib to use the append, and the last one is priority queue pull. Well, you know what, I mean, doesn't matter. And so the idea for this function is queue that we want to search for the most item. Well, let's just return it. Why not? So, like the algorithm here, we just get the first element and then we search for the one that's higher than the maximum. But if the PQ is empty, yeah, we can show an error. Oh my god. Let's delete the stuff here because it's okay. So we just, well, maybe it made sense to use a pointer. So yeah, let's do pointer to item, the item that we want to return. So here we can say 1 for the error code. Next would be to, now we know that we have at least one item, right? So we can say that the highest is the first element. So let's say, well, we can actually just use item for that, and we take 0. We might also need the index, so index. Let's first do index and then here use index. Yeah, we also need to remove the item, but that's not important right now. So again here maximum, let's say, and now for 0. When we find an item that's greater than maximum, we store it and we also keep the index. I was thinking might be nice to also have DA remove. Let's see. Define DA remove. Okay, so the idea in DA remove is that we have to go from the index that we want to remove until the end, and we shift everything to the left. So yeah, and then we decrease the count. I mean, it's yeah, probably can have well, we might implement this as a data structure itself. So just keep them as this, and then when we do the when we finish this one, we also do the nice one. So here it's return 0. So basically this is how we do this part. Or let's also do avoid a free function. So we just free the items. So now basically let's have a structure priority queue. We init, and now let's insert some values. Let's do randomly like 3, 2, 4. Let's do like this. And now let's this takes the maximum, so it should show 5. Then if we do again, it should show 4. And yeah, so let's recompile the stuff. Wait, oh, I didn't realize it was a while. So basically, yeah, it gives the items in order. Well, I mean, whatever. Doesn't matter that it doesn't work because we don't we're not gonna stick with this priority queue. We just wanted to see like the idea. Okay, so first of all, I think we might well, no, I mean, it's nicer to have this as a structure. But I don't like that here it's doing return 1. Yeah, so maybe actually can just do here return defer 1. So like try to use this macro. Let's put this higher up. So basically now it should complain here that we don't have a defer and also result. So yeah, that's yeah. So this should be fine. Now, I mean, also we could add here some error checks. Let's see, just to make this one better. So here items can be null. So after the DA realloc, we could actually check. Well, I mean, we can just use realloc here, not to worry about. Wait, yeah, because this is made, okay, like this. And here, if we get some nulls, then we can return differ one or whatever, fair to allocate memory. I think that's the only place where we can fail. Yeah, I mean, this is pretty impossible to happen. Like you just have to allocate like 100 gigabytes or something. I mean, like 16 or whatever is your limit. Okay, and yeah, basically, let's say this is also an int now. Like this is the only reason I kind of don't like that, but at the same time it's better to just have the checks. Anyway, so with those changes, we're still gonna need the DA stuff for our priority queue. So the question is, how can we implement it using, or what's a min heap actually? Maybe that's a better question to ask. So let's say we want to insert like the value 3. Well, nice drawing. The value 3. First we have an empty heap, so instead insert it at the root. It will be like a 3, right? Then we want to insert the next one. Let's say it's a 2, and we go to the first empty spot, which is this one. Now since it's a max heap, the order is right, like 3 is higher than everything else on the bottom, so nothing changes. Or maybe better said, 2 is smaller than 3, so it doesn't change. But let's say now we want to insert a 5. Well, we put it in its place, but now the order of the min or max heap is not really correct, because 5 is higher than 3, it should be on top. So we have to swap these two around. And yeah, basically, let me just do the swapping. So we swap these two values, go back to 10, 5, and 3. And now the order is again fine. And now if we want to, let's insert one more. Let's insert one, so it's simple. The one comes here, because this is the next free spot on, like this is the first one, second one, third one, fourth one. Okay. Yeah, so now if we were to insert a 7, let's say a 7, the 7 would come here, right? So the 7 must switch with the 2. I mean, too lazy to uh, let's just erase the 2 from here. So I said the 7 switches with the 2, and now the 7 must switch with the 5. So let's also delete the 5. So these three values will switch, but one after the other, not at the same time. Right, so all the values switched places. Okay, and now if you want to delete, let's say the 7, or get the maximum value, you will get back the root, so 7. Okay, and now the like the interesting thing is we no longer have something here at the top, so it's like empty right now, right? So this value is empty, and what we have to do is delete the last node. We delete it and put its value instead of the root node that we just deleted. We put it here. But now you might say, well, but this is not right. Like this is small. It should be lower than these two nodes. And yeah, basically that's the idea. Now we have to sync it back down, right, at its place. So we're gonna take a look at both neighbors on the left and on the right, and we are gonna choose the largest one to do the swapping. So we swap 2 and 5 because 5 is greater than 3. So the higher child needs to, like the highest child needs to switch places with the node that we sync. So let's delete this and this. So these two will swap now. We put the 5 on the top and the 2 here. Now again we look at its two neighbors. It only has one, but this one is smaller, so we don't need to swap again. So everything is fine. But yeah, now again, if we want to pull another node, it would be 5 because it's the root. And again, we have to move 1, which is the last node, in place of the 5. So let's quickly do that. Okay, we have to delete this node. And we have to put 1 here. And as before, this one is larger, is smaller than its children, so we have to swap it with the highest one, which is 3. So let's swap 1 with 3. We delete this, and now we put 3 here, 1 here. Now the order is fine. This node doesn't have any children, so no more syncing. Then again we delete the 3. Okay, the last node, sadly it's 1 again, so it has to swap around with, well, doesn't really need to swap around, it just goes to the top, right? So let's move 1, and again, now we look at the two children. We only have 1, which is larger. I mean, it will always be larger. You don't even need to check. Wait, not sure. Maybe you have to check, but yeah, like the point is only 1 child. You look at its value, it's higher than 1. So we need to swap them again. We swap these two nodes. So here comes 2 and 1. Now we'll get the 2. This one is deleted, and this is the last node remaining. It goes to the top, no children to check, so it stays as the root, and the last node that we get is gonna be 1. So yeah, as you see, we get everything in order. And I mean, hopefully it makes a bit of sense how we use this tree structure. And to make things a bit easier, instead of using a tree, we can use an array. And the point is that the first cell will be the first item, the next two cells will be its two children, then the next four cells, 1, 2, 3, and 4, will be these four children, then we're gonna have 8 cells, and so on. So basically the way to index, so let's do, no, the way to index a node's children is to say 2i, well, it's 2i plus 1 and 2i plus 2. Okay, so basically if we have 0, these are gonna be 1 and 2, right? The 2 here is because we, as you see, we always double the size, so right, we double the size. Then for 1 it's gonna be what, 3 and 4, so 3 and 4. For 2 is gonna be 5 and 6. So it makes sense. And to access the parent node, you have to divide I by 2. It's basically the reverse. And also not I minus 1 divided by 2, right? So for 1 it's gonna be 0, for 2 it's also gonna be 0, because this is integer division. For 3 and 4 it's gonna be 1. For 5 and 6 it's gonna be 2. So this is how we index stuff in the binary tree by using an array instead of the actual tree. So it makes things a bit easier. Let's yeah. So let's actually just remove. Well, not really. We don't really need to remove stuff right now. Let's remove this stuff. Well, actually, yeah. Let's just remove everything from this. So yeah, basically, as I said, we are gonna create like a special structure for us. It's gonna be, let's say, a node that we want to insert. Okay, it's gonna have a priority, and a void pointer for data, so we can put anything in here. And this should have a structure, or like an array of nodes. It's gonna be a dynamic array of nodes. And I was also thinking that maybe we can make the priority queue work in either like min mode or max mode by using, well, we can have like an enum, but it might be more interesting to have a compare function. And I guess even better would be to have here a void pointer and also have a function that gives you the priority of a node. So let's say here we have a compare function and a priority function, which gives you the priority of a node basically. Okay, so when we init the structure, we also need those two functions. So we just put null and then the compare and priority functions. So for our let's call it simple node, and let's say the data is I don't know, let's make it a const char pointer. Let's use like fruits or something. Anyway, so yeah, well, as I said, when we insert the value, we insert it in the last available space, so we do just the append. But after the append, we have to shift it up to its correct place. So first we need to define the result like this, then we append, but this is not really correct, so we need to have a void pointer item, and we just append it. Then here we need a defer and return result. Well, oh, it's items, sorry for that. So this should be called items. Well, we do a dereference at some point, am I right? So we actually need to send in what, a void pointer maybe. Wait. Oh. Oh yeah, it should be an array like this. I mean, since it's void pointer is the item and the other star is to indicate that it's in array. So now it should be fine. Oh, okay, so this is an item. Great. So yeah, basically now we know that the last item is just inserted, and we need to check its value with the parent. Okay. So we have to do that in a while loop. So let's say we have the index, we have the parent index. So int index is gonna be the count minus 1. Okay. And we also have the parent, which is gonna be index minus 1 divided by 2, as we just discovered. And it's gonna be, well, the comparison, let's just say the comparison is gonna be we compare the current item with its parent. If this compare is, let's say, less than 0, so this will make it depends on the compare. So if the current item is smaller then the parent, we're gonna get less than 0. So like the default compare will be a max heap. We have to swap the two items around. We swap them, and then we just have to update the index and the parent, right? Like index would become parent, and parent would become again this computation. So as you might see, like this is like a pattern which should repeat. So we can actually have here a while loop, while index, well actually this can be part of the while loop to make things easier, because on the else case we just break. So actually let's do while index is not 0 and this thing happens, we have to swap the item with its parent, right? And then update the index and update the parent. Okay. So yeah. Alright, so this will be a void pointer. Now let's just return 0 for now. Let's look at our stuff. So let's do int simple node compare, let's say max. We just compare. Well, I mean, I don't even think we need priority, the priority function, because we can use compare. Am I right? Like, do we need priority? No, we just need to be able to compare the nodes, right? Like, that's the only thing we need. Yeah, yeah, I think that's the only thing. Because we can compare, yeah, we can. I mean, it would be nice to have with the priority, but doesn't really matter. Okay, I was thinking just when we remove, put this back, we have to compare this and this, then this and this, and also these two. Well, no, we just need to compare these two actually, like most of the time. Okay, so here we need to also add simple node compare, and let's create some um, struct simple node. Let's do this. Let's just create some simple nodes, like randomly. Struct simple node apple. uh, might be easier to just do an array and have it like this. Banana. Okay, perfect. So now if we insert everything, okay, and at the end let's do a for loop that shows us like the structure itself, what's inside of it. So let's do a for loop and let's just print them. They are not really in order, so let's see what we get. So this will be like the root node, this will be the two children of the root node, and this will be uh, the children of 3. So actually it's a min heap. It was wrong about it. So let's put, that's why I wanted to check first, because it's actually like this to get a max heap as I wanted. We should have used these numbers to recreate our example. 32517. Okay. I mean, it's the same thing, we are gonna get them in order, but yeah. Well, see, it's 7 is here, then comes 3, 5, then 3, and then 1 and 2. Right, like this is the structure. Okay, so now how to get an item out. Right, so as I said, we just get this item, we kind of have to delete it. Not really, we just take it. So let's have the result, let's have the defer, and now let's say, well, if the priority queue is empty, just can't do anything. It's an error basically. Otherwise, we take the first item. We take the first. Oh, we need a pointer to, because we want to modify its value at this address. So we need a pointer. So we take the first item, we put it into our thing, into our container, and then we have to swap the first, like instead of the first item, let's put the last item, as we did in our example. We put 2 instead of 7. So now what I'm not sure. Let's say we had a 6. No, let's say we had, what if we inserted a 1 instead of 3, right? Like a 1. And here we had a 2 and we didn't have this. This would come here, and you, well, I mean, you need the maximum of these two. We need the one that's larger, and if this one is larger than and by larger I mean the compare function gives you the positive, I think, whatever. If this one is larger than that, you have to swap it with that, right? But yeah, so I think the easiest way to do it is, let's say we assume that this index is the highest, then we check the first child, check if it exists. If it exists, then we compare if we need to swap, right? If we need to swap, again, we keep this as the maximum value. And then we also have to compare this value. Again, we check if the child exists. And then if this is higher, then this becomes the higher value. So this has to be swapped with the child. So yeah, let's see. Mhm. So first we need to see if okay, let's see. So we get the index, which is 0 at first, right? Like here. We need now left. We also need right. Well, um, yeah, whatever. We can do this. I mean, we can do it like this. If left is smaller than pq count minus 1 and um, but let's see, we also need the index to swap with. Um, right, we also need the index to swap with. So let's say int swap equals still index or something. And here if left, yeah, basically if left is well, strange, index is smaller than parent. Okay, I have to check again the compare function. So this should be like, oh, this should, yeah, it makes sense to be a minus b to check for max, but maybe we made a mistake here when we put, oh yeah, yeah, like if index is higher than parent, we are gonna get positive. So if the current item is higher than its parent in a max heap, we have to swap. So yeah, it should have been greater than. So here in this case, if we have a left child, we compare the left one with the index, basically with the index, and if the left child is higher than the current index, so it's greater than 0, we set swap as the left. And here we again have to check if we have a right child. If we do, yeah, we check if the right child is higher than the current swap, which might be the left one, right? If this was true, then swap became left. So in this way we compare this one with both of them, with both of these and these. So it's one compare less, basically. And yeah, if the swap is not index, we just swap them. And I think that where should the while loop happen. So maybe it should be a do while swap equals index. Oh yeah, we also have to say, oh yeah, we already said index equals swap. So let's say we don't have any child, like 3 for example, right? We want to sync it, but it doesn't have any children. So left is gonna be, this is gonna be false, so it goes out. This is gonna be false, it goes out. So we should have maybe a do while. Let's try to do a do while. Do while swap is not equal to index. I think this should work probably. Yeah, we can check. So let's say we have a structure simple node item. We priority pull, we pull a single item. We print f pulled the item, and then we print the queue again. So let's see. So we pulled this one. Something didn't really work. Let's go into pull. Yeah, because we should also remove the last one, I guess. Well, I mean, it's a special case if we have only one item left, but we'll do that after we fix this. So, yeah, basically it left 2 here. So why is that? Let's have here a printf. Let's show the index, and let's show the swap here. So it didn't go into any of these. Let's show left. Let's show right. Maybe, so index is 0, left is 1. So it should compare this with this. The left item, the left item with the swap item. Wait, what? Okay, let's see. It's 3, so it's good. It's positive. Okay, let's print f the count. The count is 5. So what? Okay. Something's okay, so we have the count is 5. Oh, this is smaller. Well, should be smaller than count. Okay, let's do it again. So yeah, it pulled 7 and then it moved 5 here. So it's now 5, 2, 3 and 1. And here, well, I no longer have that. I should have saved it. But so it removed 7, it put 2 instead of it, and then 5 was the largest one, so 5 came here and 2 came instead of its place. So yeah, it looks exactly like in our example. Okay, so this worked fine. Yeah, so well, we actually just have to do count minus minus. But yeah, here for example, if we have only one item left, I don't think it's gonna work. So let's do and let's see what happens if we pull everything out. Oh, I still have this thing. I mean, sure, it works, right? But if we have only one item, we get it, and count minus one is still 0. So this overrides itself. No, I mean it's fine, right? Index is gonna be 0. This if statements don't work. This doesn't. We don't step into this if. This breaks, and then we delete the item. Yeah, I think it works. So so yeah. Well, like this print statement anyway. Let's also add int priority queue. Could be a peak function, but I also wanted int priority queue. Well, it's more like empty, and it checks for this thing. So now we can say no, while priority queue is not empty, we take the items, and we should take them in order basically. So if we compile this thing, we get them in order, and if we change the compare function, let's do rb ra, we get them in the mean order. So yeah, basically that works. Let's do free. We just have to do that. So if we oh, we lost some stuff. Well, I guess it's basically lost when we print items. We should also free them, free the item. Right. Okay, yeah. because these are allocations, and we do one more allocation when we do the unit capacity. So simple node, but where is the seventh allocation? Right, because I only see 1, 2, 3, 4, 5. And when we insert the first node, we do an allocation. I mean, I really need to. So yeah, this is 5 allocations. But this creates one more. It's interesting. Because it's just a realloc. But yeah, who knows? Who knows? Like, let's try to do something else. Let's comment out. Yeah, maybe realloc does 2 allocations or some stupid thing like that. Anyway. So yeah, basically now we have the min heap, or now it's a max heap, but if we change the sign, like the compare function, let's also implement the, to make things easier, min. So this is B, this is the A, and now we can have min. So now if we comment this out and run it, now we have the min heap. So yeah, basically this is everything, and I will have to pull everything out into, I'll make again like a header library, and then we are gonna use this header library in the A-star implementation. So yeah, see you next time.